Full screen this time. Okay, let's start with the. तुम्हें mute करा. One day workshop on the tuning of PID controllers. Myself Sudhir Vamne. Uh, in previous semester, we have already seen the subject called control system 1. In that, we have seen the what is open loop system, what is closed loop system, right? What are the different advantages of taking feedback from the system? And we also seen the what do you mean by plant, what do you mean by a system, right? So based on that, we also depend the regarding standard second the parameter called as a damping ratio, that is zeta, right? Zeta is nothing but what the tendency of the system itself to oppose the oscillation. You can make a note of thought. It is the tendency of system itself, the system does to oppose the oscillations, right? In certain system, this tendency may be very high. In certain system, it may be very low, or it's in certain system, it may be a moderate by nature, right? Based on that, we have categorized our system into a different classification. One is called as a over dam system, second is under dam system, third is the critically damped system, and fourth one is the undammed system. For that also we have seen the pole locations, right? Over dam means what? The value of zeta is very high, so that you will not at all get any oscillations, right? And the critically damped means what? The value of zeta is exactly equal to 1. In that case, are real, negative, and equal, right? Now for under damped case system, you will get oscillations initially, and those oscillations will get damp out after a certain time. We can see my next slide, that is time response of a second order system. The shown graph is of an underdamped system, in which initially you are getting some oscillations, right? And you can observe that automatically those oscillations are getting damped, correct? Now, for if I focus only on the underdamped system, we have defined different, or we have divided this entire response given by the system into two parts. One is the transient response, second is the steady state response, right? In a transient response, again the parameters are like peak overshoot, settling time, rise time, peak time, delay time, etc. Right? Now, in case of a steady state response, once the transient response completely vanishes, then the response, that is steady state response, will start, right? In that parameters are steady state error, ESS, correct? So you can see that C of t is nothing but the output of the system when you apply a input, that is here I have taken it as a step input having a magnitude of 1, right? Now, when you apply step input to any system, or especially standard second order underdamped system, it will produce the output like this, right? I just plotted that graph of C of t versus over a time t, correct? Now you can see that this graph starts from a origin. This graph starts from origin. It is rising, and reach to its maximum value, right? And then it falls down, goes to negative maximum, and then again these are nothing but the oscillations, right? And once the transient response vanishes, then it starts the steady state response will get started, right? Now the maximum or the largest error between the reference input then actual output, this dark black line is nothing but the actual output given by the system. This one unit step is the reference input, right? You can see here, this is what the largest error between the reference input and then actual output. Pointer this one. These are the largest error. So that's why we call it as a peak overshoot given by percent MP. Formula for that is e raised to minus pi zeta upon under root 1 minus zeta square. Right? every system will take certain amount of time to get settled itself. So that is called as the settling time. You can see here, initially it is oscillating, oscillating, oscillating. Once that output reaches or comes within the tolerance band, this dotted line are nothing but the tolerance band, plus that may be plus or minus 2%, plus or minus 5%. Once it comes under the tolerance band, and you can observe that here, this output is not going beyond tolerance band. It is always inside the tolerance band, right? So in that case, I can say that my system is settled at this point itself. That is what the settling time. It is the time required for the system to fall down within the tolerance band. Okay, so that is settling time. So obviously, everyone will say that my system should get settled within a fraction of second. सगळ्यांना याची व्हॅल्यू सेटलिंग टाईमची व्हॅल्यू कमीच लागते. इवन माय सिस्टम मस्ट नॉट प्रोड्यूस हाय अमाउंट ऑफ ओव्हरशूट, right? Even everyone expect that steady state error should be as low as possible, right? If I am applying a 1 to input as an input to the system, what I expect at the output must also be a 1, right? Now 1 input apply करतो तर 1 output मिळालं पाहिजे. This is what my expectation. But normally depends on the system. Your output or a system may not produce the output as a 1. It may produce to 0.9, 0.8, 0.85. In that case, you can see that there is something error, right? Now to reduce that error, or to reduce that settling time, or to reduce that overshoot, we are going to use some compensators or controllers externally. Okay, and in this workshop I am going to connect all those controllers or compensators in cascade with the existing plant. Cascade madhe we are seeing just a cascade compensation, right? In control system design subject also we have seen lag or lead compensators, right? Lead compensator is used to improve the transient response, that is to improve overshoot, settling time, rise time, delay time, peak time, these parameters. Now lag compensator is used to improve the steady state response or to reduce the steady state error, correct? And if you want to improve both at a time, that is transient as well as steady state, you can go through lag lead compensator, right? Now lag lead compensator means what? Lag or a lead means what? Just adding one simple pole and one simple zero into the system. Whether pole is dominating or zero, based on that we have categorized whether it is lag or lead compensator. Okay. Now instead of that compensator, we are going to use controller. Okay. Now in control system design subject also I have mentioned you that when we use the compensator, we use the compensator normally in two situations. One, system is unstable. To make it stable, we use a compensator, right? Now second case, system is already stable, but to achieve our required performance, that is if suppose I want settling time of only 2 seconds, error of 0.1 only, then I'll go with the compensators, right? Now instead of using compensator, I'm introducing now controller. Okay, so after few slides I'll explain you what is the difference between compensator and then controller. Okay, remember lag and lead compensator means what? Adding one simple pole, simple zero. ठीक आहे, त्यातल्या त्यात कुठला तरी एक डॉमिनेटिंग असतो, right? So in case of lead compensator, zero is dominating one. In case of lag compensator pole is dominating one, because it is very close to imaginary axis, right? That will decide the stability. I hope everyone knows this standard second order time response. I once again repeat, whenever I talk about transient response, then means what? I'm talking about overshoot, rise time, peak time, delay time, settling time. Fine. Now, whenever I talk about steady state response, I'm talking about only and only steady state error. Right? Now, as we are going through the tuning of PID controllers, let us start with the how actual what is P, what is I, what is D, and we'll see the its working principle also, and then finally go with the different tuning methods. Okay. So in PID controller, this is a three-term controller. What? Hello. In a, this PID controller is a three-term controller. Is proportional. P means proportional, I means integral, and then D means derivative controller. Okay. Now PID controllers are mostly used in the automatic industrial controllers. Okay. In maybe in process industry or even in you can say water filling बॉट एक बॉटल असतो आणि त्यात पेप्सी म्हणा किंवा पाणी म्हणा वगैरे भरतात इंडस्ट्री असतात ऑटोमेशन इंडस्ट्री असतात in that in those industries you can use the PID controllers. Okay. And most of the control loops, what I'm saying, control loop, whenever I'm talking about control loop, loop means what? It is just a feedback loop. If I insert a controller in cascade with the system, existing system, that becomes the control loop. Okay. So in most of the industry, that is 90 to 95% industries use the uh, PID type controllers. Okay. These controllers, how they work, these controllers receive the input from sensors or meters. Different types of sensors are there, right? Then those sensors will give a input to these PID controllers. So I hope picture is very clear. Input to a PID controller is what? Sensor. Output of a sensor. Now, and depending on a PID control function, whether you are using P or I or D or any combination, they deliver the output control signal. Okay. So PID, just imagine a PID controller block is there. Its input to that block is sensor output. Okay. Now output produced by that PID controller will be based on which type of controller you are using. ID, I can say that I may use only P, I may use only I may use only D, or I may use proportional plus integral, that is PI. I may use proportional plus derivative, that is PD controller. Which type of controller you have used, based on that, it will produce the control signal. Okay. And that control signal will goes to relays or actuators. Okay. Now these are the most common form of a feedback system and become a standard tool for precise control applications. Okay. Now you can see that plant which needs to be controlled. Okay. Plant is what? It is the part of a system which needs to be controlled. या प्लांटला मला कंट्रोल करायचं आहे. या प्लांटच्या ठिकाणी काही असू शकतो. मे बी युअर DC motor, AC motor, fan, anything. Okay. This plant I need to be controlled, and you can observe that I have connected a controller in cascade with this existing plant. Okay. Now out of the in this controller box, I'm placing my proportional, integral, and then derivative controller. Okay, this is the, can anyone tell me P, I, and D all are connected in a cascade fashion or a parallel fashion? These are connected in a parallel fashion. Here is the summing point. Okay, now you can see that I'm taking a feedback and giving back to the input. Right? Now, this process variable, हे काही terms लक्षात ठेवा. Process variable means what? The actual output produced by the system is called as a process variable. Okay, this is what the feedback signal, and the set point is nothing but your reference input. Okay, Kataka. And you can take any example. समजा एक टाकी आहे, टाकीमध्ये पाणी भरायचं तुम्हाला. ओके, सेट पॉइंट इज मे बी म्हणजे 35 फुटापर्यंत ती टाकी भरायला पाहिजे. सेट पॉइंट इज 35 फीट, राईट. प्रोसेस व्हेरिएबल 35 फूट नसेल, समजा 10 फुटावरती पाणी आहे, 10 फूटच भरलेलं पाणी टाकीमध्ये. सो प्रोसेस व्हेरिएबल इज 10 फूट and set point is 35. Okay, now the job of this PID controller is to, आता PID controller इथे काय करेल, it will open the wall, inlet wall up to 35 feet. है ना, टाकी जोपर्यंत 35 फुटापर्यंत भरत नाही तोपर्यंत तो इनलेट वॉल ऑनच ठेवेल. आणि 35 फूटपर्यंत आलं मग एरर किती असणार, 0, because set point is 35 feet. Process variable is also 35 feet. Means what? Error is a 0. Means you are getting reference input is equal to actual output. Right? In that case, your PID controller will turn off that inlet valve. Right? So you can see this controller output means what? The signal produced by this controller. Okay? And this error signal is nothing but the difference between set point and then process variable, which is actual output. Right? Now, we'll emphasize or we'll focus on initially proportional, then integral, and then derivative. ह्या तिघांचं काम काय काय ते बघूया. How they works. The proportional term, proportional, that is capital P, the proportional term applies, you can note it, the proportional term applies appropriate proportional change for error. See, this was the error here. Set point or difference between set point and process variable is the error. It will, the proportional, the output of the proportional controller is what? Will be proportional to this error. Get me? And this integral controller will take integrate of this error, and derivative will it will derivate the error signal. Okay. The integral term examines the process variable over time and offset of set point and then corrects the output if necessary. Right? कळेल तुम्हाला हळूहळू कळेल what do you mean by PID. Derivative controller, it will monitor the rate of a change, that is d by dt. Okay, the rate of change of process variable, and accordingly it will change the output when there are unusual changes. Fine. Now P झालं, I झालं, D झालं. Each parameter of 3 controllers, that is PID controllers, are adjusted by the user, by the operator, to get the desired performance from the process. Okay. If I'm using suppose all controllers, that is 3 controllers, P, I, and then D controller. So user will decide the values of proportional, integral, and derivative. User will. Now, how user will decide? He will first of all check what he exactly wants from a plant. Right? Based on his requirement, based on his or her requirement, he is going to set the values of proportional, integral, and then derivative control. Okay? आता मी एक 2 शब्द पटकन बोलून मोकळा झालो की he will set, that operator or user will set the values of proportional, integral, and then derivative controller according to his requirements. Right? तो कसं ठरवेल values of proportional, integral, and derivative? How he will calculate? Get my desired output, my proportional value should be this, my integral value should be this, my derivative value should be this. How he is going to calculate it? How to calculate those values of proportional or integral or derivative, we are doing this workshop. That is called as a tuning of PID controllers. Tuning means what? To get exact values to achieve my required performance. कळतं ना ट्युनिंग मीन्स तुम्ही बोलता रेडिओ पण ट्यून करत असता राईट मे बी 92.7 काहीतरी एफ एम वगैरे आहे बरोबर 92.7 त्या ट्यून करत असता this is also something like that. Okay, tuning of PID means what? Getting exact values of proportional, integral, and then derivative controllers to achieve my desired performance. Now focus on this PID controller. P means proportional, I means integral, D means derivative. Okay. Now normally we use the closed loop control system. Normally we use the closed loop control system. We have already seen what are the different ways of taking a feedback or making the system as a closed loop, right? And generally, as of now, we have seen only single input, single output systems. Okay, at least in the syllabus, we have seen only one input, one output. That is CISO systems. Fine. Now in PID controllers, you can see here a portion of the error signal. Output signal. The portion of the output signal is fed back. परत पाठवता. Okay. If it is proportional to the signal, means what? I am using the proportional controller. In case of proportional controller, that signal is a proportional to the error signal. And if I am taking integration of that, and I am taking derivative of that. Okay. Now based on that, we will characterize P, I, and D controller. Okay. One can use only P controller, one can use only I controller, one can use only D controller. Okay, मी बोलता बोलता बोलून जातोय, but one cannot use only integral or only derivative. का थोड्या वेळ सांगेन. Okay, you can combine also. You can combine these controllers. Okay, I'll mention you few names. Just make me correct which one is the wrong. Okay. I have a three controllers, P, I, D controller. Fine. So if I want to combine it, then I'll combine proportional plus integral. I'm giving you option, proportional plus integral, first option. Which one is wrong? You need to tell me. Then proportional plus derivative. Okay. Then third, I can club all those three controllers. I can say it as a PID controllers, P plus I plus D controller. And last is remaining, that is I plus D controller. See, I have a P, I, and then D controllers. Okay. Out of, I'll take P, I'll take I'll say this is what my PI controller. I will take P, I will take derivative controller, I'll say this is my PD controller. Correct? One more, I'll take P, I'll take I will take D also. Then I can make it as a PID controller. Okay? First combination, second combination, third combination, one more combination, that is take an integral and then take a derivative controller and make it as a D controller. Now out of these four combination, just tell me which one is the wrong combination or which one you cannot use it. Anyone? Fourth one, that is I plus D controller, because integral action and then derivative action both are opposite, right? They will cancel out with each other. Barabar? If I am using I plus D controller, integral and then derivative cancel out, action will get cancelled out with each other. याचा आउटपुट तुम्हाला काहीच नाही मिळणार ना. म्हणजे वापरून न वापरल्यासारखं आहे. हां, पैसे जास्त असतील तर तुम्ही वापरू शकता, त्यात काय हरकत नाही. पण वापरून न वापरल्यासारखं आहे. एक इंटिग्रेट करत राहील, एक डेरिव्हेटिव्ह करत राहील. ॲज अ होल आउटपुट इज 0. Correct? So this combination is not possible. That is I plus D control, because both actions are opposite. Okay? Now, fourth option I'll give you, use only P controller. You can use it. Okay? You can use only I, you can use only D. Right? काही स्लाइड थोड्या वेळानंतर I will say that you cannot use only I and then only D controller. कळेल तुम्हाला. So characteristics of PID controls, now concentrate on this one. What proportional controller will do, and similarly I integral and then derivative. Okay, a proportional controller, normally we denote it by KP. Proportional controller, it will, we have only two kind of response. Our total output response can be divided into two parts, transient and then steady state. याच्यावरतीच लक्ष द्या. The proportional controller will reduce but never eliminate the steady state error. Means what? When you introduce a proportional controller, it will reduce the error. Like my existing error is a 0.5, steady state error is a 0.5. If I introduce a proportional controller, it will reduce that steady state error maybe from 0.5 to 0.1. From 0.5 to 0.1, त्याच्याच पुढे लिहिलं आहे, but it will never eliminate. Elimination means what? Complete zero. Complete zero is not possible with the help of proportional controller. There will be certain amount of steady state error. Getting me? It will reduce from 0.5 to 0.1. It will not make it to zero. There will be certain steady state error. Okay? Next, it will increase the overshoot. It will reduce the error, but it will increase the overshoot. तुम्ही बघू शकता की कसं आहे, एका साईडला चांगलं आहे, एका साईडनं वाईट आहे. Advantage and disadvantages. It is reducing the steady state error, well and good, right? But while doing this, it is increasing my overshoot, or it adversely affect on the overshoot or a transient response, right? This is what the proportional controller. Now one can say, sir, मला जरा practically सांगा ना, proportional control म्हणजे काय असतं? Proportional controller is nothing but a simple variable resistance. That's it. Simple variable resistance. एक pot असतो ना, potentiometer pot. Introducing a P controller means what? Introducing one variable resistor. Okay. Now let I am giving you a variable resistance of like 1 kilo ohm. 1 kilo ohm is variable resistance. Initially I am keeping its variable terminal at 0. Okay. Now I'll say you, okay, now you can increase the value of resistance. Means what? I'm saying increase the proportional gain. What I'm saying? Increasing the value of resistance or a potentiometer means what? I'm increasing the value of proportional gain. This one, but I say just Kp. K means is nothing but normally a gain. that to the base P indicate proportional gain. Okay? Similarly, I can write Ki Kd also. Ki means what? Integral gain. Kd derivative gain. Okay? Now, just we have considered the 1 kilo ohm resistance. I said you increase the value of proportional gain. I mean, increase the value of resistance. Okay? इकडे बघा. मॅक्सिममली कितीपर्यंत वाढवू शकता तुम्ही? जो आत्ता मगाशी तुम्हाला व्हेरिएबल रेजिस्टन्स दिला होता 1 किलो ओमचा. मॅक्सिममली कितीपर्यंत वाढू शकता तो रेजिस्टन्स? Up to 1 kilo ohm. Correct? So more than that, you cannot increase it, no? Correct? Means what? What I said just to that proportional control will reduce the error. Okay? Let error is a 0.5. बघा नीट लक्ष द्या. Let error is a 0.5. Steady state error is a 0.5, and my variable resistance or proportional gain is a 0. Initially, I am not introducing any proportional controller. Means what? I am keeping it as a 0. Let me introduce the proportional gain and increase the value of resistance from 0 to 100. My error will get reduced. Let 0.5 to 0.45. तुम्हाला अजून समजा एरर कमी करायचं असेल तर काय करावं लागेल? You need to increase the proportional gain. You will now increase from 100 to let 500. Now let my steady state error comes to 0.3. Getting me? Increasing the value of proportional gain, it is reducing my steady state error. Now I said, okay, increase. Azun wado. What you will do? You will increase the value up to like 800 ohm. Let my now steady state error is from 0.3 to reduce to 0.2. 0.2 पर्यंत आला. 0.5 चा. Why? I have increased the proportional gain from 0 to 800. Right? मी म्हटलं अजून एक मॅक्सिममली पोहोचव त्याला. म्हणजे कितीपर्यंत तुम्ही वाढवणार? अप टू लेट 1 किलो. 1 kilo. Fine. Now let my steady state error is 0.15. But still it is not 0. 0.15 तर आहे error. 0 झालेलं नाही आहे. But you have reached to maximum value of that variable resistance. त्याच्यापुढे वाढू शकता का? रेजिस्टन्स नाही. Getting me? Now, if I talk about the same thing in a control system language, in control system 1, we have seen one very important point. We call that gain as a marginal value of gain. K marginal. You can increase the gain K up to only gain marginal value of its gain, that is K marginal. इथपर्यंतच तुम्ही वाढू शकता. If you increase more than that, what will happen? Your system will become unstable. Getting me? Why? Because few poles will shift in the right half of the S-plane. I mean, let my system K marginal value is let 50. 50 आहे समजा. Okay? Now I will draw pole zero plot also, and accordingly I will draw the step response. Okay? Let for K is equal to, I am now introducing a proportional gain. Let my gain is a 1. Let my gain is 1. In that case, my pole location will be like this. I assume it. And I'm getting output response as like this. You can see this much is the steady state error. Right? Now, if I increase this value of gain K from let 1 to let 20, 1 पासून तर 20 पर्यंत वाढवला, then my poles may shift from origin to over here, from this point to let over here. Okay. I have increased the value of gain k means what? I will get reduced steady state error. Reduced steady state error, you can say error कमी झाला अगोदरपेक्षा. But meanwhile it affects the only overshoot. Overshoot वाढला. Fine. Now again let k increase to let 40. The value of gain is now increased to 40. In that case, your poles may shift from this red point to let blue point. Now poles are complex. Okay. Now in that case, again you will get a reduced steady state error because you have increased the gain value, that is proportional gain Kp. You may get like this. Reduced error, but overshoot increased. Fine. Now finally, if you will increase to let 50. In that case, when you increase the value of gain k to 50, in that case, your pole locations are purely imaginary. You may get like this. Purely imaginary means what? Undamped. Okay. Now if you increase the value of gain k beyond 50 means what? You have already reached to its marginal value. Right now? If you increase the value of gain k beyond 50, what will happen? These poles, which are on the imaginary axis, they will now shift in the right half of S plane. Once pole shifts in the right half of S plane, then system becomes unstable. You may get output response as like this, which is unstable. Right? So keep in mind, you can increase the value of gain k only up to k marginal. Beyond that, pole will shift in the right half of S plane, your system becomes unstable. Correct? So can I say this has a certain limitation? हा एक लिमिटेशन आहे ना माझ्या अंगावरती आलेला. I cannot increase the gain k beyond k marginal. भले माझ्याकडे समजा मोठा रेजिस्टन्स 10 किलो ओमचा आहे, but if my marginal value is 1.5 kilo ohm, I cannot increase beyond that. Right? This is what one more limitation of proportional controller. Right? So proportional controller, it will reduce but never eliminate the steady state error. Disadvantage is what? It increase the overshoot, and we cannot increase the value of gain k, proportional gain, that is Kp, beyond k marginal, or else it will become unstable. System will become unstable. Okay. Now next is the integral controller. Integral controller, read very carefully. Integral controller works same as a little bit lag compensator. लॅग कंपेन्सेटर काय करायचं? स्टेडी स्टेट रिस्पॉन्स इम्प्रूव्ह करायचा. सेम इंटिग्रल कंट्रोलर विल ऑल्सो इम्प्रूव्ह दी स्टेडी स्टेट एरर, steady state response. Now you can read my first point. My first point about integral controller. Integral controller will eliminate the steady state error. Means what? Elimination. Complete zero करतो तो. 0.01, 0.02 पण नाही. कंप्लीट झिरो. जोपर्यंत एरर झिरो होत नाही तोपर्यंत तो त्याचा इंटिग्रेशन घेतच राहणार. Getting me? But while doing this, it will adversely affect on my transient response. No doubt, it is improving my steady state response. But while doing that, it will adversely affect on my transient response. You can see it makes the transient response worst. Okay. Now exactly reverse of this, because integral derivative action are opposite. The derivative controller stability of the system, and you can see my next point, it will improve the transient response. Transient response चांगला करून देतो तो, but while doing this, it is going to adversely affect on the steady state response. लक्षात राहिले point? Proportional controller, point number one, proportional controller will reduce the error but will not make it exactly zero. But while doing this, it will adversely affect on my overshoot. Okay. Now, integral controller, it will improve my steady state response. I mean, it gives me steady state error exactly to zero value. But while doing this, it is going to adversely affect on my transient response. And reverse of this, derivative controller will improve the transient response. म्हणजेच काय, it will reduce the overshoot, settling time, rise time वगैरे कमी करून देतो. पण हे करत असताना तो साइड बाय साइड स्टेडी स्टेट एरर वाढवतो. In short, it will make steady state response worst. Fine. Idea is clear regarding proportional, integral, and then derivative. हे नाही कळलं तर पुढे काहीच कळणार नाही, म्हणून मी याच्यावर फोकस करतो. Let's connect this proportional, integral, and then derivative system. Or if I summarize what proportional, integral, and then derivative controllers are doing, or how they are going to affect on my rise time, settling time, overshoot, steady state error, you can see this chart. You can see when I increase the value of KP means what? Not Kevin Peterson. It is proportional controller. Proportional, if I increase the value of proportional gain controller, my rise time will get decreased, but it will adversely affect on the overshoot. That is, it increases the overshoot and it decreases the steady state error, but not make it completely zero. Okay, and there is a there is a minor change or a small change in the settling time. That's फरक नाही. 0.15 चं 0.14 कर. Settling time वरती जास्त फरक नाही पडणार. It will mostly affect on the overshoot and then steady state error. Now next, integral controller, if you increase it, you can read this one. It is completely eliminating the steady state error, making zero. Okay. But while doing this, it is going to adversely affect on my transient response, that is overshoot and settling time. They increase करून देतो. Fine. Reverse of this, that is KD, derivative controller. You can see here, overshoot and settling time decrease होता है. चांगलं करून देतो, but steady state error वाढवतो. Fine. कळतंय? I mean, now also I mentioned you just said that you cannot use only integral or only derivative controller. Okay, only integral controller मी वापरून दाखवतो. बघा तुम्हालाच कळेल how or why we cannot use integral controller. If I want to draw the response after connecting the integral controller only, okay, let this is my C of t versus time t, and I'm applying like unit step input. Okay. Now once I use the integral controller, काय काम करतो तो? It will give me zero steady state error. Fine. But it will adversely affect on my transient response. बघा काढतो आता. Means it is making transient response worst. You will get increased oscillations. Okay, oscillation जास्त येतील आता. Fine. You can see here a lot of oscillations are there, and it will require more time, very large time to settle. and finally it will give you zero steady state error. बघा black line and blue line दोन्ही same आहेत. Actual output and then reference input both are same, means error 0. You are getting ESS 0, right? But increase overshoot, you can observe here, overshoot get increase, number of oscillations also gets increase, right? What about settling time? It requires very large amount of time to settle down. ओके. नॉर्मली म्हणजे आता जर बघायला गेलं तर इथे काहीतरी येईल लागेल 5 hours, 5 एक तास लागतं सेटल व्हायला. बट आफ्टर 5 hours इट विल गिव्ह यू झिरो स्टेडी स्टेट एरर. हे त्याचं खासियत आहे. Whenever you introduce integral controller, it will definitely give you zero steady state error. पण ते मिळवण्यासाठी खूप वेळ लागेल तुम्हाला. कळतंय? For example, if suppose I am switching on this fan, and my requirement is what? This fan must rotate at like 1500 RPM. Right? Just switch on it. Let it is rotating at 1000 RPM. Then means what? There is a steady state error. 1500 minus 1000 RPM. Correct? 500 RPM चा steady state error आहे. Then what I'll do? If I introduce only integral controller and make switch on, initially fan will oscillate in either direction, positive, negative, oscillating torque setting fan मध्ये. Okay, and it will keep on rotating 1000, आधी 1000 स्पीडला फिरेल, त्यानंतर 1001, 1002, 1003, 1004, 5, 6 करत करत 1100, 1101, 1102, 1200, 1201, 2 असं 5 एक तास जातील. And maybe मी अंदाजे बोलतो 5 तास, and after 5 hours it will give me exactly 1500 RPM. Your reference input is 1500 RPM, actual output is 1500 RPM, no doubt तुम्ही खुश व्हाल. एरर 0 मिळालं, बट ते एरर 0 अचीव करण्यासाठी किती वेळ लागला? एवढा वेळ तुमच्याकडे आहे 5-5 तास, right? This is the reason we cannot mostly we don't use only integral controller. त्यासोबत एक काम करूया, प्रोपोर्शनल कंट्रोलर पण प्रोपोर्शनल प्लस इंटिग्रल, राईट? ते पण मी तुम्हाला प्रॅक्टिकली दाखवेनच. Now as a whole you can see how the system will look now after using the PID controllers. This is what the process which needs to be controlled. I am taking feedback. This is my set point, and this will be the error value, and input to these proportional, integral, and then derivative are nothing but the error signal, and the output produced by this proportional, integral, and derivative, you can see here as a whole it is called the control signal. This signal is going to control the process, right? Now when I talk about proportional, you can see that P term will be, just read it. What is that? Kp into E of t. Obviously E of t ikkade hai na, error signal. Here is the error signal, here is the gain of proportional controller, and दोघांचं multiplication होईल, right? So output will be Kp into E of t. E of t is nothing but error signal. Kp is the proportional gain, right? Now regarding integration, it will take integration of that error. You can see Ki is the integral gain, and it will integrate over 0 to t error signal. Okay? And similarly derivative, you can see it is taking derivative of error signal. Okay? Okay, now output equation of PID controllers you can see here in a time domain. It is the output equation of additional. You can see here I'm using the summing point means what it is adding these three terms. Kp into E of t plus Ki integral E of t plus Kd derivative E of t. These are the entire output equation of a one PID controller. Okay? This term Kp E of t indicates it is a proportional. Integral E of t it indicates integral. Kd d by dt of E of t integrates it is a derivative action. Fine? Now, थोड्याच वेळानं आपण सुरू करूया प्रोग्रामिंगला. Proportional controller. The P controller usually has a steady state error, means it will not give you exactly zero steady state error. As the control gain becomes larger, जसं जसं तुम्ही KP वाढवत जाल, issue will now arise regarding the stability. कारण मी तुम्हाला आधीच सांगितलं होतं, you cannot increase the gain, proportional gain beyond K marginal. जसं तुम्ही वाढवत जाल, बघा ना आधी ते जेव्हा मी धरला होता ॲज अन एक्झाम्पल. Initially my value was 0. जसं जसं तुम्ही वाढवता म्हणजे 100, 200, 500, 800, you are reaching to that value, right? Means what? You are going towards instability. Proportional gain means what? You are going towards instability. Once you increase beyond 1 kilo ohm, system will become unstable, right? You can see here that this is I have introduced only proportional controller, only proportional control. This is my plant, right? Now you can see it will give me reduced steady state error, but it will increase the overshoot. Fine. Now see, for different values of k, for k equal to 1, for k equal to 2, that is kp here, for k equal to 5. जसं तुम्ही गेनची व्हॅल्यू वाढवत जाता from 1 to 5, you can see that error is reducing. Initially see blue, then gray, then orange. हळूहळू एरर बघा कमी होतं. Get me? But meanwhile it is increasing my overshoot. एरर कमी देतोय पण ओव्हरशूट वाढवतोय. This is what I said here. Increase in proportional gain, that is Kp, will reduce the steady state error but increase the overshoot and then stability of the system. Okay? These are the proportional controller. Now, huh? What? बाहर जाऊन काय? Integral controller now. Now integral controller, just as mentioned that integral controller will give you zero steady state error, exactly zero, but it will cause overshoot or it will worsen the transient response. You can see that I am introducing integral controller here. This is my existing plant, G of S. Okay. See what I have written here, Ki into 1 by S. Ki is nothing but what? Integral gain. Fine. Out of 1 by S indicates that is the integration. Right? 1 upon S is the integral action and multiplied by S is a derivative action. Right? You can see here for different values of tau I, what is tau I? I'll tell you. You can see that integral control is giving me reduce steady state error. While doing this, it is increasing my or it is adversely affecting on my transient response. Next is a derivative controller. You can observe here. This is what the Kd into S multiplied by S means what? That is derivative action. Kd is the derivative gain. You can see here for different values of derivative controllers. It is reducing my steady state overshoot But meanwhile, while doing this, it is increasing the steady state error. Advantage पण आहे, disadvantage पण. Now, proportional controller, by only employing proportional controller, steady state will occur. Obviously, it will not tend to exactly zero. Conclusion काढतोय. So next possible combination, because we are not going to use only I or only D. So obviously we need to go through the combinations. Right? Proportional तर झालं. Yes, you can use only proportional controller. But only I, only D is not possible. Next is the proportional plus integral action. The response becomes more oscillating because I have used the integral controller and needs longer time to settle. आता जसं फॅनचं उदाहरण दिलं होतं, it may require 5 hours to reach its final value. Longer time to settle, but definitely error will disappear. Error will get eliminated to zero value. Fine, this is proportional plus integral controller. Now next possible combination is proportional plus derivative. The response becomes less oscillatory. Oscillation कमी करतो derivative, but error वाढवतो. Fine. Now last and best, obviously, you are using all three terms together. P plus I plus D, that is proportional in PID controller. याच्याने तुम्हाला जे पाहिजे ते मिळवता येईल. All design specifications can be achieved through PID controller. Okay. Now, before proceeding to the actual PID controllers, let's have a tips. Thumb rules set kai hai for designing the PID controllers. How to set or how to calculate the values of KP, KI, and then KD. Okay. So first of all, do one thing. Obtain an open loop response. Given a plant, just apply input, take output. Don't make it closed loop. Open loop. I just plant gya, tela input apply kara, output gya, and determine what needs to be improved. आता ओपन लूप सिस्टमच घ्या, त्याला इनपुट अप्लाय करा, आउटपुट बघा कसं आहे. तुम्हाला वाटत असेल की आउटपुटमध्ये काय 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 चेंज करायचं ते लिहून घ्या. सपोज इफ यू वॉन्ट टू रिड्यूस द ओव्हरशूट, इफ यू वॉन्ट टू रिड्यूस द स्टेडी स्टेट एरर, ते नोट डाऊन करून घ्या आधी. ओके. नेक्स्ट, ॲड अ प्रोपोर्शनल कंट्रोलर टू इम्प्रूव्ह द राईस टाईम. आधी तुम्ही सगळ्यात सुरुवातीला PID मधलं डायरेक्ट I आणि D वापरू नका. आधी प्रोपोर्शनल कंट्रोलर वापरा. त्याने काम होतं का बघा. त्याने काम नाही झालं, देन इंट्रोड्यूस अ इंटिग्रल कंट्रोलर. त्याने काम नाही झालं, देन इंट्रोड्यूस डेरिव्हेटिव्ह कंट्रोलर. देन इट इज add a proportional controller to improve the rise time. Then add a derivative controller to improve the overshoot. And add integral controller to eliminate the steady state error. Now adjust, you need to adjust each value of KP, K and KD until you obtain desired output response. Here's adjustment. जे आहे ना, मी शेवटचा पॉईंट नंबर 5 लिहिलेला आहे. काय सिंपल एका शब्दात लिहून मोकळं झालं ते. Adjust each value of KP, K and KD until you obtain a desired output response. जोपर्यंत तुम्हाला जे पाहिजे, म्हणजे ओव्हरशूट एवढेच पाहिजे, राईस टाईम एवढंच पाहिजे, स्टेडी स्टेट एरर एवढंच पाहिजे, हे जे काय तुमचे रिक्वायरमेंट आहेत, जोपर्यंत ते मिळत नाहीत तोपर्यंत तुम्ही काय म्हणतो तो KP, K आणि KDची व्हॅल्यू ॲडजस्ट करत राहा. KP बदलून बघा, मिळालं का, नाही मिळालं, ठीक आहे. KI वाढून बघा, मिळालं, अजून नाही मिळालं. KD वाढून बघा, मिळालं, अजून नाही मिळालं. KI कमी करून बघा, KP कमी करून बघा. दिस इज वॉट कॉल्ड एज अ ट्रायल अँड एरर मेथड. ओके. प्रत्येक वेळी ट्रायल अँड एरर मेथड पॉसिबल नाही, कारण आपल्याकडे थोडा वेळ नसतो. राईट. दॅट्स वाय देर आर फ्यू मेथड्स टू ट्यून दी PID controllers. Tune the PID control means what? Obtaining the exact values of KP, KI and KD to achieve our required specifications. यासाठी बाहेर पैसे घेतात एक PID कंट्रोलर ट्यून करायला. ट्युनिंग मीन्स वॉट? जास्तीत जास्त काय करून देतात, ते आल्या विचारतात तुम्हाला नेमकं पाहिजे काय हे सांगा आधी. तुम्हाला ओव्हरशूट एवढं पाहिजे, एरर एवढं पाहिजे, ठीक आहे थांबा. ते काहीतरी मेथड्स असतात त्यांचे ट्युनिंगचे मेथड, ते अप्लाय करतात. ते अप्लाय करून झाल्यानंतर दे विल से कीप द व्हॅल्यू ऑफ के पी के अँड के डी टू दिस व्हॅल्यूज यू विल अचीव युअर रिक्वायर्ड स्पेसिफिकेशन. दॅट इज कॉल्ड द ट्युनिंग ऑफ PID कंट्रोलर्स. फाईन. Please wait. Now let us consider, let's start with the MATLAB programs now. Prior to that, let me open the MATLAB software. Online students, any doubt? Online students? Pranav? Okay. Now you can see here, I'm assuming let my open loop transfer function, what I'm saying, my open loop transfer function is g of s, which is equal to 1 upon s square plus 10s plus 20. This is my open loop plant. आता याचं मला आउटपुट रिस्पॉन्स काढायचा. कसं काढता येईल? वी हॅव ऑलरेडी सीन दिस इन कंट्रोल सिस्टम 1 ऑल्सो. मॅटलॅब ओपन होईल. Okay, I'll take a new script in MATLAB. First of all, I need to mention what is S. The G of S घेतला होता, त्यामध्ये S काय आहे ते मेन्शन करावं लागेल, because MATLAB don't know that. S is a integral part of transfer function. So just I'll write S is equal to TF of S. Okay. Then my next command will be directly what is G of S. G of S is equal to G is equal to see, G is a 1 upon S square 10s 20. I'll type the same 1 divided by S square plus 10 into S plus 20. Na? 20. Okay, this is what my transfer function. Now I will say same. Take a step input, apply to the system and give me. Apply to a system means what? Which system? To a G and give me its response. Okay? See. I need to save it somewhere. You cannot save it as a 1. Value level. Now level again. Okay, I will run it now. You can see it will give me tf is also variable. tf कमांड वापरलाय ना मी, त्यामुळे त्या फाईललाच नाव tf देता येणार नाही. So here you can see that you applied a unit step input, correct? This is what the output response given by this open loop system. But remember here you are applying a unit step input to the this plant. So output must also be a unit step, right? ज्या अर्थी वन इनपुट देता है आउटपुट पण वन असायला पाहिजे. This is what your expectation, correct? But you can see that this blue line is nothing but output response given by the system to the step input. It is settling at 0.05 only, बरोबर. अप्लाय किती केलं वन, गिविंग म्हणजे आन्सर किती आहे 0.05. मीन्स वॉट, देर इज व्हेरी लार्ज एरर, 0.95चा एरर आहे. वन अप्लाय केलं मिळते किती 0.05, 0.95चा एरर आहे. दॅट एरर हॅज टू बी रिड्यूस्ड, करेक्ट. Just S is equal to TF of S and G equal to what? 1 divided by S square plus 10 into S plus 20, right? Give me step response of G. I will save this. As let SSW. I need to delete this one. I'll save it as a SSW. कल चुकते का 1 upon so this is what the step response here. Wait, it's really busy. You can see it is settling to a value 0.05. There is a large error and this error has to be reduced. No doubt oscillation nahi hai. Huh? So what I'll do, I will now introduce some controllers to reduce the steady state error. So I know that proportional controller can reduce the steady state error, right? So the proportional control reduce the rise time, increase the overshoot, and reduce the steady state error. That's why I'm using the proportional controller initially. Okay, what I'm doing is I'm just connecting one proportional controller that is having a gain of a Kp in cascade with the G. Okay, and when I connect the Kp in cascade with the G, this overall system, this Kp will get multiplied with the G, right? So that let transfer function is by G0, G to the base 0. Okay. So again I will write a MATLAB program. काय करावं लागेल बघा जास्तीत जास्त. These two commands are same. S equal to TF of S. Then I am introducing G. I need to write what is Kp. Kp ची value किती पाहिजे. Let randomly we'll take assume as a Kp value is 300. ठीक है. Kp 300 है. I have stored that variable. Now I will define what is G0. G0 is what? Kp into G. G0 is G into Kp. Right? Now finally, I will now calculate the step response of this entire closed loop system. आता मी closed loop करतो. युनिट फीडबॅक आहे. कोणाला कोणाला फीडबॅक येतो G0ला, राईट. सो माय चेंजेस विल बी, बघा, changes in the existing MATLAB command is what? Once I define the G, I need to define what is KP. KP is here. Let's assume that 300. My G0, which is nothing but KP into G, correct? Now next, to define an overall closed loop system, I use a notation as like T. T is a closed loop, G is a open loop. T is equal to what I'm saying, take a feedback from G0, value 1 means what? You take unity feedback, right? And finally give me step response of not G, give me step response of T. Right? Now you can observe here, reduce steady state error. See, आधी oscillation नव्हते, बरोबर ना? Before introducing the proportional control, oscillation नव्हते. After introducing the proportional control, oscillations आले. See here, my statement. It increases the overshoot. Okay, but it will reduce the steady state error. See, error किती होतं आधी 0.95, म्हणजे ॲक्च्युअल आउटपुट किती होतं 0.05. तुम्ही अप्लाय केलं तर 1. आता बघा किती मिळत आहे. हिअर इज द 1, हिअर इज द फायनल आउटपुट. इट मे बी 0.95, 0.93, right? Even you can calculate steady state value. You can see here steady state error is, final value is 0.938. So 1 minus 0.938 is your steady state error. बघा आता error 0.95 चं अगदी 0.07 पर्यंत आलं एरर. रिड्यूस झाला एरर, पण 0 झालं का? नाही. 1 इनपुट अप्लाय केला तर 1 आउटपुट मिळालं का? नाही. कळतं? दिस इज व्हॉट द प्रोपोर्शनल कंट्रोलर. Now next we'll verify for different values of Kp. For different values of Kp, yeah. See, note down करून घ्या कोणीतरी, नोट करून घ्या. For Kp equal to 300, for Kp equal to 300, overshoot is 40%, 40. For Kp equal to 300, overshoot is 40. And final value is 0.938. Final value is 0.938. Fine. Now if you increase the value of Kp, what will happen? Your ESS will get reduced, but percentage overshoot will get increased. Correct? ESS decrease means काय? Your final value will get increase, because anyhow final value means actual output. तो वाढला तरच error कमी होणार. Okay? And reverse of this, if you decrease the Kp, what will happen? ESS will get increase. I mean final value reduces, barabar? And similarly overshoot will also get reduced. ठीक है? For Kp equal to 300 तुम्ही note down केला. What is ESS or final value and then overshoot. Now I will change the value of Kp to from 300 to 100. Fine. See, this is what my output response. Now you can see peak response and then steady state error. Overshoot by किती आहे? Now overshoot is 20%. बरोबर? जसं म्हणजे याचा अर्थ काय, जसं तुम्ही प्रोपोर्शनल गेन वाढवत जाता, ओव्हरशूट वाढत चाललेला आहे. व्हॉट अबाउट फायनल व्हॅल्यू सी हिअर इज नाव 0.833. फायनल व्हॅल्यू कमी झाला म्हणजे काय, एरर जास्त आहे. जसं तुम्ही प्रोपोर्शनल गेन वाढवत जाल, आता इथे मी उलट करतो, प्रोपोर्शनल गेन कमी केला, 300 to 100 केला. खरं म्हणजे मी आधी 100 घेऊन मग नंतर 300 एक्सप्लेन करायला पाहिजे होता. सो फायनल व्हॅल्यू हळूहळू वाढत जाईल, एरर कमी होत जाईल, बट ओव्हरशूट वाढत जाईल. दिस आर दी प्रोपोर्शनल कंट्रोलर. Fine. Now I will introduce proportional and then derivative controller. Derivative बघूया आधी. नंतर then we'll go for PI. Okay, see here proportional plus derivative controller. Proportional पण आहे, KP पण आहे, and meanwhile derivative पण येणार, that is KD. Okay, again I'll take same example. G हे तर आहे KP is equal to let 300 and KD is equal to 10. See, getting these exact values are nothing but what tuning. ते थोड्या वेळानं शिकवतो मी. KP is 300, KD is 10. So in that case, you can see here, I am introducing KP as well as KD. Right? Multiplication of this along with G is a G0. And finally, I'll take feedback, unity feedback. Right? So KP equal to 300, let KD equal to 10. So G0 will be equal to what? G into this. Right? Into this means what? Yeah, control में कौन कौन है? Proportional plus derivative. Proportional means what? KP. Plus, you can see here, one more term, KD into S. Into S means what? That is derivative action. Divided by S means that is integral action. It is multiplied by KLM. That's why I am saying this as a derivative controller. Okay? So, KD equal to 10 now. I'll introduce. KD is equal to 10. KP is 300. Na? KP is equal to 300. Now G0 will be equal to G into KP plus KD into S. Right? K na KP पाहिजे. KP plus KD into S. Right? Now again take a feedback, then give me step response. I can see. Derivative controller काय करतो? Derivative controller, it will improve the transient response. You can see here. आधी ओव्हरशूट किती होता? 20% ना? 40 20 होता. ओव्हरशूट बघा कमी झाला, 15.3. Improved the transient response. But while doing this, it is going to adversely affect on my steady state response. आता तुम्हाला एरर जास्त मिळणार. .938. Fine. For different values of KD, you can see here. For KD equal to 10, for KD equal to 20. I'm getting for KD equal to 20. You can see. या दोघांमध्ये फरक बघा काय, कोणामध्ये ओव्हरशूट जास्त आहे, फॉर 10 or 20? ओव्हरशूट. ऑसिलेशन्स बघा, KD मध्ये जवळपास 1.25 ऑसिलेशन येत आहेत, KD मध्ये एकच ऑसिलेशन येतं 20ला. राईट? Means it is improving the transient response but adversely affecting on my steady state error, because you can see here हा पॉइंट बघा आणि हा पॉइंट बघा, एरर वाढतो. Now next is the proportional plus integral. Integral controller, see the integral controller, that is KI, it will decrease the rise time, increase the overshoot and settling time. Means it is adversely affecting on transient response, but it will eliminate the steady state error. Error तुम्हाला नक्की 100% 0 मिळणार. 1 इनपुट दिला तर आउटपुट 1 मिळेलच, पण हे करत असताना ऑसिलेशन जास्त येणार. ठीक आहे? Let the value of Ki is a 70. I'm considering different example. 1/s² 10s तेच आहे का? Let Kp equal to 30 and Ki is equal to 70. Now you can see here I'm introducing proportional plus integral. Proportional is a Kp and integral is Ki divided by S. Divided by S means what? That is integral action, right? And overall, this entire thing multiplied by G is nothing but G0. Okay? So Kp equal to 30, Ki is equal to 70. Now, instead of Kd, I'll use Ki. Okay? Now, instead of into S, it must be divided by S. Ki divided by S. कन्फ्यूज होऊ नये म्हणून एक काम करा, ब्रॅकेट सेपरेट ब्रॅकेट करून घ्या. व्हॅल्यूज काय होते? Kp equal to 30, Ki equal to 70. Fine. Now you can see, as I am using integral controller, error will be 0. One input apply केलात, one output 100% मिळणार. You can see output exactly to value 1, right? But while doing this, it will take more and more time. आता बघा किती वेळ लागतो बघा, इथनं 0 पासून ते बघायला गेलात तर इथे सिस्टम कुठे सेटल होतो. इट इज टेकिंग 2 सेकंड. 2 सेकंड पण खरं म्हणजे खूपच जास्त झालं. इट इज टेकिंग 2 सेकंड टू सेटल डाऊन. म्हणजे नॉर्मली आपण काय म्हणतो की विदिन फ्रॅक्शन ऑफ सेकंद सेटल व्हायला पाहिजे, पण तरी हा 2 सेकंद घेतो. आता तुम्ही म्हणाल सरांनी मगाशी तर 5 तासाचं उदाहरण दिलं, इथे 2 सेकंद पण सरांना जास्त वाटतं का? नाही, पण कंट्रोल सिस्टम भाषेत 2 सेकंद सुद्धाही जास्त आहे. ओके, कारण ॲटोमेशन इंडस्ट्रीमध्ये सेकंड टू सेकंड सगळं खूप फरक पडतो. फॉर एक्झाम्पल, कोका कोला कंपनी आहे, त्या बॉटलमध्ये समजा कोक भरत आहेत आणि इथे समजा तोटी आहे आणि तिथनं कोक पडतो आहे आणि बॉटल इथे आहे. अँड लेट अज्युम दॅट टू रीच दिस बॉटल टू एक्झॅक्टली ॲट दिस वॉल समजा एक 7 सेकंद लागतो आहे. कन्व्हेयर बेल्ट आहे, 7च्या ऐवजी त्याने 8 सेकंद जरी लावला जायला चुकून, 7 सेकंदानंतर ती तर तोटी ओपनच होणार ना, कोक पडायला लागेल. ॲज्युमिंग हा बॉटल तिकडे पोहोचलेला आहे, पण ह्याला तर 7 सेकंद नाही 8 सेकंद लागत आहेत. मग काय होईल? 1 सेकंदासाठी कोक खाली जमिनीवर पडत राहील. कळतंय? मग किती किती नुकसान होईल. Now you can see for different values of Ki. So effect you can see here. जसं जसं मी Ki ची व्हॅल्यू वाढवत चाललोय तसं तसं ऑसिलेशन जास्त मिळतात. मीन्स वॉट, इट इज ॲडव्हर्सली अफेक्टिंग ऑन माय transient response and it is taking more and more time to settle down. Now tuning of PID controllers. Now how to get exact values of PID controllers. Okay. Before starting to this different or in short I'll say tuning of PID controllers. You all know closed loop and open loop systems. Based on that, these methods are categorized: closed loop methods and then open loop methods. After एक फक्त नाव बघूया आपण, then we'll have a lunch break, then we'll continue. All these total 10 मेथड आहेत. 10 पैकी एक 4-5 जरी पाहिलो आपण, एक तुम्हाला एक रफ आयडिया जरी आली तरी पुष्कळ आहे. आय से 100% इफिशियन्सी आहे या वर्कशॉपचा. 4-5 मेथड जरी व्यवस्थित कळले तरी आउट ऑफ 10. सो क्लोज लूप मेथडमध्ये बघा, जिगलर, निकोल्स, ऑल दीज आर सायंटिस्ट. जिगलर होता आणि निकोल्स होता, ह्या दोघांनी मिळून एक कंबाईनली मेथड डेव्हलप केला टू ट्यून दी PID कंट्रोलर्स. Normally it is also called as online continuous cycling or ultimate gain method also. Then त्यांनाच कळलं की काही वर्षानंतर अरे आपलं असं असं चुकलं होतं. त्यांनी त्यांच्या अल्गोरिदममध्ये चेंजेस केले. Then they said that now we are come up with the modified Ziegler-Nichols method. Then Tyrus-Levin method, damped oscillation method. Then Ziegler and Nichols worked in the open loop systems also. Then Cohen-Kuhn method, CHR मेथड हे कोइन कून आणि अजून एक सायंटिस्ट आहे. सो दीज आर डिफरंट मेथड्स ओके टू ट्यून द PID कंट्रोलर. आणि तुम्हाला थोडंसं जरी की यू आर स्टील ॲट अ अंडर ग्रॅज्युएट लेवल फक्त वडी मीन बाय PID कंट्रोलर एवढंच आहे. सो ट्युनिंग ऑफ PID कंट्रोल मे बी ते कुठे असेल इफ यू गो थ्रू फॉर अ हायर एज्युकेशन दॅट इज पोस्ट ग्रॅज्युएशन दॅट टू इन अ कंट्रोल सिस्टम स्पेशलायझेशन then ha part in tuning of PID controllers. Different methods to tune the PID controllers. But I hope I already completed my master degree in control system. So sharing with you is well and good at early stage, that is at an undergraduate level. आत्ताच तुम्हाला कळलं, नंतर तुम्ही कुठेतरी जॉबला जाणार, ऑटोमेशन इंडस्ट्रीमध्ये जाणार, तिथे गेल्यावर तुम्हाला सांगता यायला पाहिजे. इफ सपोज ॲटलिस्ट हां एवढे मेथड आहेत, दिस इज हाऊ वी कॅन ट्यून द PID, ते लोकही इम्प्रेस होतील. Right? So these are the different methods to tune the PID controllers. After having a lunch break, we'll continue the Ziegler-Nichols method. सोपे आहेत, डोंट वरी. खरं म्हणजे अवघड आहेत, पण मी तुम्हाला सोप्या शब्दात समजावून सांगेन. We'll have a lunch break up to 1:15, half an hour. हां 1 वाजता मेस कुठे तुम्ही या ना तोपर्यंत. Okay, online students, is it okay for lunch break up to 1:15? Online students? Okay. You can leave the Google Meet now and we'll gather at sharp 1:15. Okay? जे लाईव्ह ब्रॉडकास्टिंग असतो तो पॉज करता येत नाही का? नाही. हं?